this video focuses about junction field effect transistor. So in this paper, the basic diagram is the structural diagram of JFET. We can call it JFET in its abbreviated form. And as we can see here, the PNP, but we do not call it as a PNP transistor, but rather we call it as N-channel junction field effect transistor. PNP is named for the bipolar junction transistor, but in case of field effect transistor, we name it as N-channel for this type, and we have another P-channel JFET. So we are considering here N-channel JFET, and about its structure, the whole structure is a P substrate, and it has got two sides. That is p-type semiconductor, and that's a kind of substrate to this body. So the basic terminals of this JFET is, this is drain, and these two ports are gate, and this is source. So the basic idea of working of JFET is the electric field across this gate controls current through this path. This is the basic idea of working of junction field effect transistor. And so we are going to talk about how does this works. So in this case, we have connected the two p-type gates are made a common terminal, so that we have three terminal device: gate, drain, and source. And in this setup, we have made a P and source. We have connected this gate part and source with this voltage source. This may be a small, we can consider that. And we have another circuit that goes from drain and a voltage source, and that's connected to the source. So we can name this as VDD, and we can say this as VGG. So since this source is connected to drain and source, so this value we can consider as VDS, voltage across drain and source. In the same way, we can consider this source, since it has been connected to the gate and source, so this may be equivalent to VGS. Okay, so how does the electric field across gate terminal controls current through this path? We can consider this as channel. So at the beginning, we forget this source. We are only considering the whole body of the JFET. So in the initial setup, what happens is, since this is N-type and this is P-type, there must be a depletion layer. So these are bound charges that are distributed throughout this depletion layer. So at the first point, we are considering VGS is equal to 0 volt, and let us suppose VDS is 1 volt. So at that point, in this case, gate voltage is 0, so we can consider the circuit normally flowing through this part to this part as electrons. So what happens is, due to 1 volt, electrons from this side are pushed towards drain side. Electrons, and current ID is obtained, and that flows throughout this circuit. So our task is, what happens to the current when we increase the VDS to a significant amount. So for example, 5 volt. At 5 volt, what happens is this source terminal is at 0 volt and this terminal is at 5 volt. So the voltage difference between this gate and to this region is same. So voltage difference is 0, but the voltage difference between this gate terminal and to this region of this JFET is 5 volt, and that we can consider as reverse biased diode. So what happens is the depletion layer is spreads more towards the drain region than the source region. So this is the case. So why does this happen? There's a basic idea about this. For example, we can consider this path as a linear resistive path. So what happens is, since this is 0 volt and this is 5 volt, we can consider there might be a region where there's a 1 volt, there's 2 volt and 4 volt to the all the way to 5 volt. So in this region, this is 2 volt and this is 0 volt. So the negative reverse biased condition to this region is less than the reverse bias condition to this region, because this is 5 volt and this is 0 volt. So this junction is less reverse biased than this junction. So the area where more reverse biased is found, the depletion region occurs more to that region. So as we go on increasing the VDS value, let's say 8 volt, then a situation occurs at which the the region increases so significantly that the region from the two sides touch each other. So at that time, what happens is we have a technical term for that situation, and that's called pinched off situation. And what happens to that situation is the channel disappears. Channel means the path for the flow of electrons. So at pinched off condition, the channel disappears and further increase in ID current is stopped. So does that mean that the current flows down and decreases down to 0? No, that's not the case, because if the current goes down to 0, then there must be there won't be voltage difference between this path, and the depletion layer will decrease again, making a free channel, and again current will flow. So there is a, we can say that there kind of equilibrium establishes. So from the 0 volt increasing to 5 volt, current significantly increased, and when we made VDS equal to 8 volt, then current became pinched off, and at that situation current cannot go further higher and becomes constant, and that current is called saturation current. So I have another graph describing about, okay, let's say in second condition we can consider VGS is equal to minus 2 volt. So that situation, this is minus 2 volt and this is 0 volt. This is already in reverse biased condition. So what happens is when we apply a negative field to this gate region, the reverse biased condition increases more significantly, and at the same value of 5 volt, the depletion layer will increase more than the previous one when the VGS was 0. So in this case, without reaching VDS to the 8 volt, current gets pinched off at the voltage less than the previous VDS. So let's say in this case, when the VGS is minus 2 volt, let's say VDS is at 6 volt plus 6 volt, the current gets pinched off. That means when we apply a negative voltage to the gate terminal, then current gets pinched off at a smaller VDS value. So the saturation current decreases as we increase the negative gate voltage. So that's the conclusion. Okay, let's see the graph that I have made. Okay, this is the graph. As we can see here, I was talking about the saturation current, and that point is this reason. We can call it saturation point. So the corresponding value we can plot here. So as I mentioned earlier, when the VGS value was 0, the VDS value we increased all the way to 8 volts, and at that point the current got pinched off and it could not increase furthermore and remained saturated. And when we increase the negative gate voltage, then saturation current decreases. And the basic idea about getting pinched off is reverse bias condition occurs more faster in negative voltage, as I mentioned earlier in my previous diagram. So when VGS is minus 2 volt, then current gets pinched off at even a smaller value, and when VGS is minus 5 volt, then even smaller. And one condition occurs when the negative voltage is large enough that the current cannot increase more significantly to the drain, from drain to the source terminal. So that condition is called cutoff condition. So this is all about drain characteristics of JFET. Thank you.